Hello, wonderful people of the internet. Welcome back to another episode of Simuleos. Let's see, what do we have here? Nick, Pratik, Gibbous, Comic 47. You have way too many E's, man. Thank you guys so much for coming in. And anyone who might be lurking in chat, hey, thanks for being here. Hello, recently joined a Henry Stickmin roleplay server. I'm now the head of a security for renowned criminal organization, the Topat Clan. I feel like I saw someone playing Henry Stickmin not too long ago, but I don't remember. Maybe it was Markiplier? I don't really remember. I don't usually watch Markiplier or people like that, but I do specifically remember this one this one game in particular. What do you mean sorry? I mean, have you not met? That's my only personality trait is that I'm sorry for everything that I do. Like if you take that away from me, I have nothing. So you know that's what I mean. Anyway, let's do output here. Perfect. Okay. Your personality is page, new page before. I have a question. How do you feel about getting E'd every stream? I don't know. I don't understand it, but also I don't mind it. I guess it's fine. I don't know what E means, you know? Like, is it like epsilon? Like, or I don't know what it means. I'm sorry about that. But it's fine. Like, it's totally okay. Same with like why Bachuleo says I'm a cinnamon roll. I don't know why it says I'm a cinnamon roll, but whatever. It's okay. The exercise rewards aren't available. How else am I supposed to waste all my channel points? I'm not doing it today, but I might be able to do it tomorrow. Honestly, like, again, I broke my toe a while ago, and, like, I just haven't been able to do the workout stuff regularly. But it has been getting a lot better, so I feel like maybe tomorrow it'll be a bit better. But we'll see. Okay, so let's go. I want to give you guys a quick update, because a lot happened this weekend. Like, an insane amount of stuff happened this weekend. Let me just go ahead and go here. There. Okay, perfect. So what's going on? So I, maybe, accidentally started like 3 new projects over the weekend, of which I can do none of, but I just wanted to talk about anyway to see what you guys thought about. So, right. So on the list of things that I do and I should be doing regularly, one is YouTube, right? For which we're starting a new series, which is Problem of the Week, where we just basically talk about some sort of research problem every week. And this week we're going to talk about like how to tell if you're attracted to the Sierpinski Triangle, all related to fractal compression, eventually hopefully creating a state-of-the-art fractal compression method that people haven't seen before, but we'll see. Right, so this is kind of my YouTube thrust right now. Then, of course, we have the algorithm archive, which I'll put in blue. 2 is the algorithm archive. Look, I'm massively behind on anything to do with the algorithm archive. I've got like 10 chapters I need to write, and I'm not writing any of them. Then on top of this, I of course have my own work stuff with Grant and 3 Blue and Brown and the Summer of Mathematical Exposition and all this kind of stuff going on. There's a lot of stuff going on there. So then this weekend, my friend was like, hey, do you want to make a game? And I'm like, yeah, sure, I'll make a game. Yeah, that seems totally fine. Yeah, I definitely have enough time to make a game. So now we're trying to make like a spiritual successor for Guild Wars, which is like, it's not going to happen. Like, there's no way. But like, I figure I should at least give it a shot so I can learn some game development. But then, you guys may have forgotten, a long time ago, I created a project called Scribbleos. All right, hear me out. So I kind of stopped making stuff for this year. I stopped making like writing content for a while. I was getting into game dev after hating game dev for years. Yeah, look, I know I'm not going to enjoy the process, but at the same time, I feel like I don't know. Like, I wanted to give it a shot. Like, I don't know. We'll see. You guys know that there's like one game that I like, which is Guild Wars, and this is basically a Guild Wars game. And essentially what had been happening was over the past week, I really spent too much time playing Guild Wars 1, and I was like, screw it, you know, I'm going to spend all that time that I have been spending playing Guild Wars and put it into game development, so at least I'm getting something productive out of it. And that was kind of the idea. Let me go here, let's see what we got. Paste this here. Perfect. Game programming patterns. Do you struggle to make your code hang together with cohesive whole? Yeah, nice. Yeah, this is good. Probably. I don't know. Okay. Let's see, what do we have here? Seems like stretching yourself too thin? Wait, stretching yourself, Sim, like butter scraped over too much bread. Yeah, no, I agree with that. That's why I wanted to talk about what I'm going to do about it. Also, question, can we add TI-83 implementation of Monte Carlo algorithm to the algorithm archive? Is it already there? When are you going to write a well-documented, physically accurate physics engine? We badly need a good one. Oh boy, look, I don't want to touch physics. Anyway, my point was, on top of the game development, I also have Scribbleos, which is where I'm writing a bunch of like fiction, essentially. I actually went back and I read some of this, and I was like, man, I actually really like some of the stories that I wrote. Yeah, a lot of it is, maybe not particularly great, but I was writing it every day for a while, and I really wanted to get back into it and just write a story. So I had a whole bunch of story ideas planned, and then finally, for some reason, number 5, I just decided to make a webcomic. Now let me just explain. Let me just explain really quick. The webcomic was particularly useful because a lot of times when you're trying to describe something, you end up in this weird phase where you're like high text density but low image density. But a lot of times when you're trying to describe something, you want to be high image density, low text density. So I was like, how about we make a webcomic that is exactly that? It's just like a, high, image density. We describe everything as cleanly as we can, but then we also have like, comic-esque captions and stuff like that to enable, just to kind of help people along here and there. So here's what I made some executive decisions. 1, I am not going to be making the webcomic. Okay, now I know I just introduced it and I said I'm not going to do it, but the thing is, it's just been on my mind for a long time. Like I had plans for this. I wanted to call it subroutine, which would mean like, it's a routine for me to make comics like every day or every week or something like that. So subroutine is also a function call, and the idea would be that it's like, just kind of a daily comic where we talk about like, weird algorithms and stuff like that. Decided not to do it just because, again, just no time for that. Now, in terms of the other things, YouTube, definitely have to keep making YouTube videos. Definitely got to keep making algorithm archive articles. I still really, really want to be an author. Like no matter how deeply I tried to deny it. Like every time I start to write, like I genuinely enjoy writing. And game development, again, I don't really want to do game development, but here's the thing. This game, the plan for the game is actually for users to like, you're basically creating a meta language for this game for users to like, basically code up their own AI. You can kind of imagine it like Adam 13131's like Botland type of thing, except the idea is kind of closer to like a henchman from Guild Wars 1, so you kind of like code up the interactions between players and stuff like that. And so in some sense, creating this kind of like meta language for how to play the game is kind of interesting. And so I do find that actually compelling enough that I'll probably do it. But this is kind of where I'm at. So obviously I have too much on my plate and I just keep adding new projects. But I think I created a schedule so I can actually do everything and go from there. Let me go ahead and catch up on chat. When you're going to write it well documented, I'm not going to do anything with the physics engine. I'm so sorry. I probably should, but I'm not going to. Game programming has different requirements than other software, so there are different patterns, and the canonical patterns are used in different ways. That's probably fair. I don't know any of it. Well, my friend suggested TI-83 algorithm, and he said it was denied, and I was like, bruh, and now I'm here. Wait, TI-83, you mean an algorithm written on TI-83? We definitely have TI-80, like 4, right? So I assume we have TI-83 as well. Gibbs just said that as well. Okay, so your stories are cool. You should publish them in an ebook or something. Yeah, so here's the thing about writing. Like, I genuinely like love writing so much that I just can't get away from it. So just real quickly before getting started with the research stream, let me hop in here and just say, so I had like a bunch of ideas for stories. I think what I might do is kind of something that I did a while ago where I might just like hop into writing every now and again. Like, before we had writing Wednesdays, but maybe like as we're just closing up stream, we just spend an hour just to do some sort of writing, whether that be for the algorithm archive or whether it be for fiction or something like that. Again, I realize this isn't everyone's cup of tea. Gibbs in particular said he doesn't really appreciate those streams, and I get that. But at the same time, I really do enjoy writing, and I think some of the stories were really good. Some of them weren't, but some of them were quite good. And I do want to try to turn it into a full novel for something to publish, and just to kind of flex that creative muscle a bit. And I think, part of the reason why I was like so excited to do the webcomic is that for the past month, I had not been writing. And because I hadn't been writing, I kind of was missing that kind of creative energy, Can I access the algorithm archive site? I hope nothing broke. Yeah, it works fine on my end. It's still algorithmarchive.org. Here's the link. I can put it over here. It seems to work on my end, but maybe something happened. So anyway, just letting everyone know that, like, again, Might do some more fiction on stream a bit later. Anyway, let's go ahead and hop into what we're doing for today. Just wanted to update everyone on the other projects journal, new page before. Dark Box, you just came at the perfect time for me to explain what exactly I'm doing. I literally just started, so... okay, so a long time ago, not a long time ago, like last week, we jumped into the concept of fractal compression. Fractal compression. Now, okay, there's a lot to say. There's a lot to say about like fractal compression and how it works and why it works and all this kind of stuff. For the most part, what we need to know is the following. It takes some sort of image, it turns it into a set of equations that we can use known as a Hutchinson operator. And then it will allow us to basically take a lower resolution image, so this is low res, read it into the Hutchinson operator and get the same image out. Okay, so I didn't do a very good job of explaining that, but basically the idea is, here is that we have the ability to take any image and turn it into a set of equations, essentially. And then because we have a set of equations to like dictate what the image looks like, we can then basically use a low resolution form of the image, put it through the set of equations to get the image back out. And this is how we can compress our data. It might be a pull request. So github.com, 1 second, algorithm archive. Like it could have just been that we didn't have anyone to review it. So it might not have been that it was denied. It's just that we didn't have anyone, TI 83. Yeah, so we just didn't have anyone to review it, so we had no idea what to do about it. Or maybe we did. Oh, no. I tried to review it, and like no one, and they didn't update it, so we just kind of left it. So if your friend wants to come back, and they want to like look at the pull request again and like respond to the comments, then in principle we should be able to get it merged. But right now it's kind of in limbo. Because again, I think we were just waiting on a response from the commenter. In fact, I think maybe what I was going to do is I was going to split that PR up and just like do it on my own. But I just had no idea what to do with that. All right, see Cosmic, have a wonderful evening. So this is the idea of fractal compression. Again, we take an image, we turn it into a set of equations, and then we allow ourselves to basically read in a low resolution image. And that's where the compression comes from. So let me go ahead and remove this for now, because right now we're actually kind of going to hop into another topic a little bit. So let's go here, delete that. Did you implement the fractal compression algorithm? Not yet, because we're still way, way behind. And so I'm going to talk about where we're actually at with this. So here's our logic. Here's where we've gotten to. Oh my gosh, I can't speak. Here's where we've gotten so far. 1, fractal compression exists. Compression exists, but it's beaten out by JPEG. Like basically every other compression method just beats fractal compression. So the questions I have are: 1, can we compress better? Can we compress better? Which I have ideas of how we can do this. But also, can we speed up compression? Can we speed up compression? Right. So these are kind of the things that I want to talk about, right? Can you teach us about this with 3D images? We can do we could do 3D, but I think that makes it a bit too confusing. So we'll go into 2D images in just a bit. I don't know if we'll be using anything to do with Voronoi. Actually, Voronoi. I can't pronounce that word. Anyway, I don't think we will. Okay, so these are the questions that I have that I want to answer. Okay, so to get there, one thing that we want to do is a GPU accelerated, GPU accelerated fractal compression method, which means, I guess if we want to do GPU acceleration, we have to accelerate 2 different things. The first thing we have to accelerate is, of course, the fractal compression itself. But a core component of the fractal compression is a subtopic known as the chaos game. Okay, so let's talk about what the chaos game is. I'm going to hop down here, and we're just going to create a set of equations. So function 1, actually let's create 3 points, point A, point B, and point C. And this is a stereotypical example with the Sierpinski Triangle, not Voronoi anything, but it's a different type of triangles. Okay, so here we're going to do F1 is going to be equal to whatever your point location is plus A over 2. F2 is going to be equal to point plus B over 2. And F3 is going to be equal to P plus C over 2. If we start with any point in space, doesn't matter where, let's just say here, and we choose a function at random, it doesn't matter which function we choose, just as long as we're doing it at random, we might move halfway towards A, and then halfway towards C, and then halfway towards B, or something like that. Eventually we'll find that we land on some area or some component of the Sierpinski triangle, okay? And once we've done that, essentially the point is now attracted to the triangle. It cannot leave the triangle. Every future iteration will be on this shape. And the idea here with the chaos game is that, again, we can generate these random shapes, and I'll show you exactly how we do it in a second, by just kind of randomly sampling this set of functions with some sort of random point. I am writing on a Wacom tablet. So that's the idea of the chaos game. Now, the way this works is inherently iterative. We start here, we go there, we go here, we go there. So it's one step at a time. And the reason that this is so difficult to do, the reason that this is so hard to do in parallel, is because parallel methods, parallel things, don't do very well with, like parallel hardware like GPUs, don't do very well with iterative things. So the question is, how do you speed up something that is inherently iterative? And we have ideas of how to do that. So, that's the question next, is how exactly do we speed up the chaos game? Okay, but see, this led to a third question, which is the question we're going to tackle today. If we can speed up, let's say, the chaos game in a massively parallel way, well, one way in order to do that is to make use of the parallelism of the GPU, which means instead of doing one single point and having it move 1,000 times, we might take 1,000 points and have them all move a fewer number of steps. But like I said before, if we start off the triangle and we move, via these random functions, we're going to get closer and closer to the triangle every step. But the question is, how much closer do we get? How do we know when we're actually on the triangle? And these are the questions that I'm actually asking right now. So the third question, and the question that I want to tackle today, is how to tell if you are attracted to the triangle, to Sierpinski, right? So that's my question. How do you know if you're attracted to a particular attractor versus another attractor, right? I don't mind slow compression if it's effective. In my Amiga days, doing an 8-hour compression was acceptable, and I can pronounce Verneuil too. I'm sorry. But yeah, so we're literally talking about like 5 hours of compression versus like 30 seconds for JPEG or something like that. Like we're talking about like a factor of like 20,000 improvement for using other compression methods. So the question of can we speed up compression is actually very important here, because the question is, not only can we speed it up, but can we make this particular method viable, right? Only one step in the triangle can be out of the set. I don't know what you mean by that. Sorry about that. So let me go ahead and get some water. And then I can show an example of the chaos game. So let's go ahead and CD into projects. Actually, I'm just going to go into videos, algorithm archive, iterative function systems, ls here, and just run mpv Sierpinski chaos. .mp4. Okay, so what you're going to see here is actually a generation of the Sierpinski triangle via a chaos game, where we just did like 10,000 points, and we're just showing them like in batches of like 1,000. No, we did like a couple million points, I think, here. I don't remember how many points, but we did a huge number of points. And we're showing them at like 10,000 at a time or something like that. So then we pick a random point, let's just say the center of the triangle, and it will just kind of move around a bit until like, maybe about here, it looks like it's on the triangle at this stage. And then from there, basically everything else will be on the triangle, right? But, just saying that it looks like it's on the triangle isn't really a particularly good error metric. And it's actually remarkably difficult to figure out what a good error metric is for this particular system. So that's kind of where we're at with that. So Darkbox, thank you so much for following. Really appreciate it. Yeah, so Sierpinski Triangle is the set. And what I'm saying is, with chaos games, you typically ignore the first 10, 20 steps or so, with the assumption being that after the first 10 or 20 steps, you're on the triangle, right? So then the question is, well, if you're on the triangle after 10 or 20 steps, how can you verify that you're actually on the triangle? That's the question. Hey, Summit, how are you? Anonymous Cheer, thank you so much for the bit. Really appreciate it. So yeah, that's what we're going to try to answer today. There isn't actually a good answer to this. Like, I've been searching for a very long time for an answer. I'm going to do another quick Google search just to make sure I'm not completely stupid. But let me explain why there isn't really a good answer for this. Actually, I think I can just drop an image of the Sierpinski Triangle in there. Perfect. It's not the best image, but that's okay. Let's move this over here and over there. So this is our Sierpinski Triangle, right? Like what D just said, the Sierpinski Triangle isn't, we see triangles, right? Like if you look at this, it looks like a triangle. I can just draw a line from this point to that point, and this point to that point, and this point to that point. Totally fine. Like we see a bunch of triangles. But in actuality, the Sierpinski Triangle isn't a bunch of lines, right? It's actually a bunch of points. So if I were to like zoom in on this particular section right here, and maybe make it this big box over here, you know, what we'd like to see is maybe, I don't know if I drew the right area, but maybe something that looks like this, you know, where we have the triangle going in here, and then here we have, you know, a subtriangle, and here we have a subtriangle. You know what I'm saying? Like, I'm not very good at drawing this, but, you know, this is what you'd expect to see, a bunch of lines that look something like this. But again, it doesn't have any area or anything like that. Essentially what this is a bunch of points, right? So we see, let's do that in pink, I guess. I see that green is just like the orange, whatever, it doesn't matter. So yeah, it's essentially just a bunch of points along these lines, right? So asking ourselves the question, you know, how far off is a single point from the Sierpinski Triangle is actually rather difficult, right? So let's say we start with a point over here, right? And we're just trying to find the distance D, here, D. Well, okay, it's going to be hard because like this distance D isn't really going to be from anything, right? Because there isn't going to be a there's not going to be a point like directly centered, tangentially from the triangle, right? Like it might be off a little bit. So if we're looking for point D, we might actually do a close approximation to this closest point instead of from the triangle itself, right? And so this is kind of like the hard part here. Doing good. Thanks for asking. What about you? I'm doing okay. Thanks for asking as well. Hey, Verse Libre FM, how are you? I hope you're having a great day. So that's kind of why the question of like, how far away is a point from the triangle is kind of like, there isn't a really good question for that. What we can ask is, how far away is this point from any other point on the triangle? That's simple enough. So let me just, because it is kind of a semantic difference. So one, the question of how far away is point P from any point on the triangle, that's relatively easy. But the question of how far away is point P from the triangle, that one's actually very difficult to answer. Because again, the triangle is just a set of points. And so we can find like, you know, how far away is it from the closest point. But if we're looking for from the attractor itself, well, we don't really have the attractor. We just have a bunch of points that look like the attractor. You can calculate the convex hull and then the perpendicular intersection of the lines. Right. So that's the thing. That doesn't really work exactly because let's say, you know, let's say that our point isn't outside of the triangle. Let's say our point is like right here, right? So if our point is like right there, then doing the convex hull doesn't really make sense. And again, specifically for the Sierpinski Triangle, there is a way to do this, right? Verse Libre FM, thank you so much for following, really appreciate it. Okay, so like for example, with the Sierpinski Triangle, what we could do is we could just split the triangle into 4 sections. One triangle up here, and I don't remember who came up with this, but someone in chat mentioned this. So we could split it up into 4 triangles, 1, 2, 3, and 4. And we could just consistently split the triangle up again and again and again and again into these set of 4 triangles until eventually our point is on like element 4 of the mini triangle in here, right? Does that make sense? And so like once we find that it's part of that space, then we can say, okay, so how far away are you from any of these other triangles, right? And so for the Sierpinski Triangle, there is a way to do this. But for general attractors, I genuinely couldn't think of any. I spent hours on this, like genuinely spent not only hours on stream, but also like literally like 5-6 hours over the weekend, just racking my brain, trying to think of good ways to do this. And I just didn't. And admittedly, you know, I didn't spend the whole time, you know, thinking specifically about this one problem, right? Like I was kind of mixing, you know, a bunch of different problems in, trying to figure a bunch of stuff out at the same time. So there could be something obvious that I missed, but the fact is, again, because the Sierpinski Triangle is a set of points, not a set of lines, You know, I also thought about maybe doing some form of like, what's it called when you take a bunch of points? Linear regression or something like that to turn it into a bunch of lines. But even then it didn't really work because, you know, how are you going to do that with something like, you know, these points in here? Like, how do you know, for example, that this set of lines or these set of points here are all along that line and that you shouldn't include any of these points over here, you know? Like, it gets really messy and I couldn't quite figure that out. So what I'm going to do right now, just to make sure that I'm not missing anything completely obvious, because again, I was just kind of pen paper thinking. I wasn't really like Google searching or anything like that over the weekend. Let me just Google, you know, error terms on chaos games, and let's see if we can find anything really quick. So error terms for chaos games. And if we can find anything related to this, I'm more than happy just to read through it, try to figure out what we can do with it. But the problem is every time we talk about chaos games, we always get all of these like incredibly like naive implementations of it. Let's see. Okay, never mind. I can't really answer that right now. So 1 second. Once it's on the attractor, it can't leave the attractor. Right. So here's one way in which you could do it. So what you could do is you could take a single point. Take random point. Okay. Then you do, you know, 1,000 iterations. Well, just say 100 to 1,000 iterations. Okay. So if you do 100 to 1,000 iterations, then what you can then do is you're basically certain that this point is now on the triangle, right? So then you can be sure that every single point after that will also be on the triangle, right? And so then you can be fairly certain that you know, any of these points that you generate after the first 1,000 iterations are on that triangle. So if you want to do this in parallel, like we eventually want to do, where you're going to run it 1,000 times through, you could just, you know, create your set of points such that all the points are already on the triangle. So you could like pre-compute all of those points. And then you could just, you know, use children from the point that's on the attractor. I'm not doing a very good job of describing that. Let me try to explain that one more time. 1 second. What on earth? What's going on? Oh my gosh, 1 second. My side chat just got really mixed up. Right, it is still messed up. Let me try. How do you what is going on? I guess that's fine. Whatever. Doesn't matter. I'll figure that out. Anyway, so the point is, if you take a random point, you do 10 to 1,000 iterations of the chaos game, you will be on the triangle, right? And in general, for any attractor, you can kind of assume that after doing 100 to 1,000 iterations, you're going to be on the triangle. Or on the attractor, whatever that attractor is. It doesn't necessarily have to be the attractor. So then the question is, what if we do have a more complicated attractor? And there isn't really a good... Oh, for Pete's sake, it's driving me nuts. 1 second. Just give me 1 second, guys. I'm so sorry. My side screen is really messing up, and I can't see anything. So, just 1 second. Sorry about that. Here, there. Okay, perfect. Should be fixed now. Yep. Okay, it's fixed. Okay, so, right. So I was just saying, after you do 10 to 1,000 iterations, whatever, you're going to be on the triangle, and that means every point from then on is going to be on the triangle, right? This doesn't really help us figure out how far any random point is away from the triangle, because again, even though we have 10 to 1,000 points on the triangle itself, is the stream down? The stream shouldn't be down. It says it's still live on my end. I'm so sorry. It looks like it's still live. So I think we're fine. I think it's still up. Okay. I've been trying to say the statement for like 10 minutes now, and I haven't been able to do it. So let me try it one more time. 1 second. There. Okay. Yeah, it looks like it's still up on my end. Okay. So, if we have a bunch of points that are on the triangle, right? That helps us a bit, because that means if we're trying to find this distance d, we can definitely find the answer to number one, how far away point P is from any point on the triangle, because we will have points on the triangle, and we could just kind of sort all these points based on the distance from D. Now, that's going to be an awful sort, because we're going to have like 100,000 to 200,000 points that are all on the triangle, and we have to do, we have to sort all 100,000, 200,000, 10 million of them, or something like that, in order to get a good approximation. It's not the best way to do it, but it is a way to do it. So what I was trying to say here was that, so I think that's all I was trying to say there. How exactly do you want it to be? You could calculate a few 1,000 points and then find the closest and zoom in on this point, etc. I'm hoping, I really want it to be as exact as possible, but I know that's not going to be the case. So my main issue with this is, again, what we could do, for example, so again, what I mainly have in mind is parallelism, right? So eventually we're going to run into this case where we have, 1,000 different processors all doing their own kind of computation on their own, right? So this means instead of starting with 1 point and doing 1,000 iterations, you're going to have like 1,000 points, all doing, maybe 100 iterations or something like this. Now, the question is, how do we first generate that set of 1,000 points that we're going to read into that new chaos game, right? And this is where my question comes in, because if we have 1,000 points, we run a chaos game 1,000 times. That's totally fine, and that will get us there. But one thing that we have to be careful not to do is to take 1 point, do 1,000 iterations, and then use that point 1,000 times, right? Because for some situations, like with the Sierpinski Triangle, it doesn't matter. But with some cases, like for example, the Barnsley Fern, I think this could actually run into some issues because the Barnsley Fern has different probabilities for each function to be chosen, right? So there's one function that, for example, can only be chosen like 0.1% of the time, or sorry, 1% of the time. It has a 0.1 probability of being chosen. And so, like for example, that particular point might be like a point on that particular section might make it harder to like spread out to the rest of the fern or something like that. I don't know. I mean, I guess maybe I'm thinking too much about it because, if it's a random point, if the chaos game works with any random point, then that too could technically be a random point. And so in principle, it should also be fine. Yeah. I mean, maybe that is a solution. Maybe I'm just overthinking this, and maybe, the actual solution is just not to worry about error terms on chaos games. Everyone knows that chaos games are inherently messy, so we just leave it at that. It's just, again, for the case of, I didn't save it, I deleted it for some reason. For the case of fractal compression, well, I mean, the attractor is this weird 2D image that is, like, very difficult to, like, describe, and so... I'm trying to think, probably having some sort of error term on the chaos game is actually really important there, isn't it? Yeah, has to be, you would think. Anyway, let me get some more water. I mean, what I'm ultimately hoping to do is the following. Journal new page before. Take an image. Okay, let's try that again. Take an image and turn it into essentially an iterative function system, right? And what I want to try to do is I want to make it so this iterated function system is basically just an analytical form of the image itself. So we don't have to keep like a lower compressed version of the image. If we have a good enough representation of the image in some sort of equation or something like that, then in principle, we should have no problems just using that form that is, just a set of equations to recreate the image via some sort of chaos game, right? Now, I think the main reason people didn't do that before is that, for example, if you have to do shading or something like that, like here's a bubble and I don't know, like it's shaded back here and is maybe light up here. I can't really pretend I can draw. Well, in this case, like you're going to need a whole bunch of points to represent this area, but very few points to represent this area. It just gets kind of complicated. So the question is, how exactly do you do that drawing and stuff like that? It ends up becoming kind of complicated. But I'm sure there's a way to also represent that. But maybe we talk about that later. Like maybe we don't worry about that for now. Like that's a problem for the future. Right now the question is, how accurate can we represent any image via a set of equations? And that's kind of where we're going with this. Okay. So I'm going to go back to trying to find some sort of error term on a chaos game. Again, I don't think you can find this particularly easily. And then we're just going to do it kind of an incredibly naive way, just to get some sort of error metric and see, like how far away a point is from, like, we're going to do something really stupid and we're just going to see like how close a single point gets to the Sierpinski Triangle or Barnsley Fern after every iteration and see if it decreases by a constant amount or not. I don't think it does. But maybe it does, and I just don't understand that, So that's something I'm going to try to figure out. Like, does every step of the chaos game, I know it brings you closer to the attractor, but the question is, does it bring you closer to the attractor in a way that you can actually measure? Like, do you know that every time you run this function, you're going to be like 33% closer to the Sierpinski Triangle? Is that something that you can like actually measure? So that's where I'm at with that, and that's what I'm going to try to do. Again, let me get a little bit more water. Super thirsty today. Okay. Chaos theory, I think, is completely different than... Well, is it, though? Maybe it is the same. Right, so we're not going to talk about, like, strange attractors and stuff like that. I think the Lorenz attractor should be a form of... let's see. Is a system of ordinary differential equations first stated by Edward Lorenz. It is notable for having chaotic solutions for certain parameters. Right, okay. I think so. What is the difference? Okay, I'm gonna say something stupid here. Let's see. Set D. What do we have? Open this. Paste here. Chaos game revisited yet another but trivial proof. Right. I have no doubt that the algorithm is correct. But if you look at this and you read it, it basically says up to infinity iterations. Where is this? I actually read this just recently. Right. So. It says down here, based on like Borel's law of large numbers, we have that with probability 1, the limit as m goes to infinity, that we do land essentially on the attractor. I don't know if this is the right equation for that, but that's essentially their argument. After an infinite number of iterations, you will be on the attractor. That's definitely true. The question is, how do we approach that limit? How many points does it take to get to, like I know an infinite number will be a solution, but the question is 10 infinite? Like, is 10 enough points to be on the attractor? Or do we need 100 or 1,000? And how do we measure that for different attractors, right? Like, I naively feel like it will only take maybe 10 or so iterations to be close to the attractor on the Sierpinski Triangle. But I feel like if you have a much more complicated attractor, then I naively feel like it's going to take a few more iterations to get onto that attractor. That's, again, I have no... It's just my gut feeling. I don't know if that's correct or not. But I want a way to verify that, and right now I don't have a way to verify it at all. So, but yeah, this is actually a good link. I recommend that people read it if they're interested in like more of a rigorous mathematical definition for chaos games. Paper on the archive on the convergence rate of chaos games seems related. Perfect. Thanks for that. Let's Google that. If we choose a different point each time, the error diminishes. If we choose a different point each time, yeah, that's something that we need to test. Okay, let's go here. Paste this, and we should be able to find... Oh, okay, that should still work. On the convergence rates of chaos games. When was this published? No way this was published in 2021. Are you kidding me? No way. Okay, well, let's... I guess we can download the PDF. We cannot download the PDF. Oh, no, we can download it. Let's take a look. What's the worst that could happen? I am seeing a lot of math, but not a lot of... Okay, well, let's take a look and see what we can read from this. This seems like something that... The problem here is that, like... I was hoping for a more computational approach. Here's probably what we want. Okay, good. So let's just read through this and see what we can find. So we... Okay, CD into downloads. Okay, PC man FM. And then I want to do, how do I sort this? For Pete's sake, I can't use a UI to save my life. Okay, so let's do ls minus a. What is it? ls minus s? How do I tell, like, when we downloaded something? Okay, how do I... Downloads, page, Qt browser. I just don't know how to figure out what I just downloaded. That's my issue. Sorry about that. ls later. CD downloads. ls latr. Perfect. Okay. Let's go here. Run it one more time. Oh, there it is on the conversion. Oh, it's just perfect. Okay, so we're gonna do Zernal on the convergence rate of chaos games. Zernal pp. Okay, there we go. And let's just take a look at it. I'm gonna move this back over here. Maybe one more. No, that's right. And let's move it over here. Scroll in a bit. That should be fine. Okay. I don't know who this guy is, but let's see what we have here. So, Belaz Bareni, Natalia Jurgo, and Istvan Kulazavari. What's interesting, though, is that this was published, like, it's on the archive in February 2021. The reason that's interesting is that, like, that was, like, 2 months ago. I just wasn't expecting to see anything that recent for anything related to Chaos games, which kind of leads me to believe that this isn't their primary research focus, that they might be focused on something else, which is totally fine. But I just want to read what they're saying and see where we're getting at. So this paper studies how long it takes the orbit of a Chaos game to reach a certain density inside the attractor of a strictly contracting iterative function system, of which we only assume that its lower dimension is positive. That's actually a very promising start, because I think that's exactly what we're looking for. So we show that the rate of growth of this cover time is determined by the Minkowski dimension of the push forward of the shift invariant measure with exponential decay of correlations driving the Chaos game. Okay, let me just highlight that as something to come back to later, because I don't understand it. We show that the rate of growth of this cover time is determined by the Minkowski dimension of the push forward of the shift invariant measure with the exponential decay of correlations driving the Chaos game. Moreover, we bound the expected value of the cover time from above and below with multiplicative logarithmic correction terms as an application for Bedford-McMullen carpets. We completely characterize the family of probability vectors which minimize the Minkowski dimension of Bernoulli measures. Interestingly, these vectors have not appeared in any other aspect of Bedford-McMullen carpets before. Whew. Okay, this is going to be a tough read. Okay, it seems more on target. It probably is more on target. Those are words. They're words. I don't know what a push forward is. So the thing was, like, of all these words, Minkowski space, Bedford-McMullen carpets, Bernoulli measures, all this kind of stuff, the thing that got me, the word that got me, that made me realize I don't understand this paper, is push forward. Like, everything else, I was like, okay, it's like, I understand this. Yeah, okay, this is fine. I kind of get it. But somehow, push forward were the ones that got me. And I was like, nope, I don't understand that. Okay. What I'm going to do is kind of scan through it and see if there's something in particular that we need to cover here. I'm looking for some sort of measure. I mean, honestly, these people probably do it in a much more rigorous fashion. We probably should be reading through it in way more detail. The problem is, there's a lot of mathematics here that I know I'm going to struggle with. Okay, let me just see what we have. 3 Bedford-McMullen carpets in red, and the images of one under the maps in each array function system. In each case, the dimension is minimized by a different vector p, see table 1. Okay, let's just read through the introduction. Well, no, they didn't seem to have an introduction. They seem to go directly into iterative function systems. No. We're literally just now getting into the structure of the paper. Oh no, how long is this? This paper is, I mean, it seems relatively well, like, it looks fine. It's 30 pages long. The parameter space of vectors, oh no. That's gonna be an interesting read. Let me go back over here, and let me just take a look at this paper really quick. Where are we? We want to grab this guy, and what I want to do is I want to look up, I'm going to look up the authors really quick, just to make sure that this is a paper we should be reading, and also I want to go to Google Scholar and see what they're kind of it say in here? It's already cited by 4. Oh, wait a minute. Oh, 2012. Oh no, this is the wrong one. 1 second. That's the wrong paper. Thank you. What's the right paper? The right paper is where is it? Someone mentioned it. On the convergence rate of the chaos game. In fact, let's just Google that. On the convergence rate of the chaos game. On the convergence rate of the chaos game. Okay. On the convergence, yeah, this is all 4 versions. It's still an archive preprint. Yeah, okay, seems fine. So let me just take a look at these guys just to see where they're from. I mean, University of Technology and Economics, associate professor, fine. Interesting, but I guess fine. Yeah, I mean, H index of 32. This guy knows their stuff. Sure. They must be at Boston University, I guess. Yeah, cool. Oh, sorry. I didn't realize someone had sent me a message on LinkedIn. I probably should not have opened that. Chaos game optimization, novel meta heuristic algorithm. This also could be something to look at. Good. Okay. So that means I kind of trust the authors. They have a relatively high H index. Like, they should in principle know what they're doing. Now is the question of kind of just getting through the paper and making sure that it makes sense. And the question is whether we should do that on stream or if I should do that off the stream. But we'll kind of get to that in a second. Where'd my paper go? Did I delete it on accident? It looks like I did that. Okay, so let's go ahead. CD into downloads. Zernal PP. And then on the convergence rate of chaos games. And move this over here. See what we got. So I'm gonna read through it a bit. See what we need to understand from it. And actually, I'm just gonna see if the math is like too overwhelming or not. It could be, it might not be. You know, who knows? 1 second. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, just feel free to let me know, and I'll totally address it as soon as I see it in chat. Outside of that, I think we're probably good to just 1 second. Maybe just to try it out, see what we can do with it. Again, it might not be perfect, but it should be okay. Unknown Sheep, thank you so much for following. Really appreciate it. Sorry, I'm looking at my side screen here because I've got some. Yeah. Okay, should be good. So we're going to read through it, see what we can do, at least get through the introduction, and if it seems just way over my head in particular, then I will probably leave from there. On the other hand, I need to get better about reading the mathematical notation of papers like these. Like a lot of this stuff I just don't know, and I should know, and I need to get better at that. So maybe this will be an opportunity for me to learn how to do that, you know? Okay, so the Chaos game is a simple random iterative procedure introduced by Barnsley 3. Yeah, so Barnsley, if you guys don't know, he's the same person that made the Barnsley Fern. It's always interesting to see people who, like, you know the name of, appear in actual papers that you're reading, to generate the attractor of an iterative function system, which is a tuple, f of f1 to n, of contracting transformations on Rd. Rd is just the dimension that you're at, so 1, 2, 3-dimensional space. Given a fixed non-degenerate probability vector p is from p1 to pn, the game starts from an initial point x0, chooses a random function fi of 1 from f, where that's going to be your set of functions. I have been calling this the Hutchinson operator. Hutchinson. And I'm curious to see why they didn't mention that. So let me actually look up Hutchinson operator. I might have been using that wrong. Okay, what do we have? Hutchinson operator. In mathematics, the study of fractals, a Hutchinson operator is the collective action of a set of contractions called an iterative function system. The iteration of the operator converges to a unique attractor, which is often self-similar, fixed set of the operator. I'm interested to see why they didn't call it a Hutchinson operator. Is it because it might not be a unique attractor? Hutchinson showed in 1981 the existence and the uniqueness of the attractor A. The proof follows by showing that the Hutchinson operator is contractive on the set of compact subsets X in the Hausdorff distance. Yeah, I need to learn more about that as well. Definitely need to learn more about it. Like, I don't even really know what the Hausdorff distance is. I should, though. Anyway, let's keep going. 1 second. Where am I? I wanted to go here. So again, I think what we want to read with this one, I don't know if we should go through this proof or not. I feel like maybe we should. Is Hutchinson for uniform maybe? Could be. I always thought that the Hutchinson operator was just what you call the set of functions. I know this is the wrong paper. I actually wanted to go to this paper. This is the proof. I don't know if we actually want to go to, like, if we want to go through this proof or not. I think we can get the gist of the proof. But what I wanted to see if these guys call it the Hutchinson operator. Yeah, they call it the Hutchinson operator. Come on. I'm not a complete idiot. Okay, let's keep going then. Okay. So given a fixed non-generic probability, P, we already read that. Let's see, it continues iteratively generating a sequence of points, x, 2, 3, blah, 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 where xn is equal to f of n, f of I of n, x of n minus 1, and the indices I are independently and identically distributed according to P. The attractor, lambda, math notation for something I don't know. What's the side cup mean? People who know math, please help me out. What does this mean? I should know, but I don't. Within of some sort? Like, I know that this is within. So we're saying the lambda is... it must be... It's not... So it must be, like, at least this dimension, right? So this... Yeah, subset. So, yeah. So when it says lambda is a subset of RD, what it means is that lambda could be 1, 2, or n dimensions, where n is the size, like the dimension of the set of functions that we're working with. Okay, totally fine. I'm just gonna write that out, equals subset. And we're gonna keep going because there's gonna be another one just coming up that I don't know either, which is the unique non-empty compact set satisfying lambda, and this is the like combination of all the set functions. So usually when you're creating, you know, this set of functions here, you're basically using this big U operator to just say, look, you know, it's a combination of all these functions. So this tuple can be described by this statement in here, this big U. Okay, is then almost surely, regardless of the starting point, obtained as the omega limit set of the orbit, x of n of infinity, i.e. lambda, again, being the attractor. I'm gonna have to write that down. Attractor. Okay. Lambda is, and this is the one I don't know what the big, like, what's the upside down cup mean? So lambda is this symbol from M1 is to M infinity of intersection. Okay. So next follow-up question, what is an intersection? Thanks, by the way, Learning Balance, for helping with that. I should be better, but I'm not. So then we say x of n, and then n is greater than m. So I knew that big U was a union. I didn't know what upside down U was. What is in all of the sets, which makes it easy to remember. So U is a union. You combine everything together, and then the intersection must be okay. The unique thing that's in both sets. So what here we're looking for is what is unique between. Okay, and what's this mean? What's this line over these two statements mean? So x of n colon. What is this saying? I'm sorry, guys. I'm asking you guys all these stupid mathematical questions because I don't understand math. But I'm trying. I really am. Bar means a closure. Okay. Follow-up question. What's a closure? Yeah. So I thought negation, but I'm like, no, negation doesn't make any sense. I think closure is probably correct. So I'm so sorry, guys. And what's the colon mean? Okay. So let me get some water again. Okay. Closure is the smallest closed set containing that set. Okay, closure is the smallest closed set. I really should take a set theory class, apparently, because apparently I just don't know any of it. Is the smallest closed set containing that set. So, okay, so the set here is x of n, where n is where's n? N is defined as which iteration we're on, I guess. And then I suppose that's saying where n is greater than m. So closure is the smallest closed set containing that set. Basically, you add in all the limit points. Okay. I think I understand what it's saying. So what we have here is we're saying that the attractor. Let me just reread this sentence. So the attractor lambda, which is a subset of RD, which means again it's either 1, 2, or 3-dimensional, whatever. If your space is 3D, then the attractor must be at most 3D. It could also be 2D or 1D. Why do they insist on making things difficult to read? I'll get to that in just a second. So the attractor, lambda, is a subset of RD, which is the unique non-empty compact set satisfying lambda is equal to the union of all these functions put together. Again, that's the Hutchinson operator. Acting on the attractor itself is then almost surely, regardless of the starting point, obtained as the omega limit set of the orbit of x of n of infinity of n equals 0. So the orbit here must just be a selection of points, i.e. the lambda, again the attractor, is equal to the intersection of m equals 1 to infinity of x of n, where n is greater than m. Dang, okay, I got a little bit lost there. Okay, let me read some stuff. If you know the notation, it makes it easier to read. Right, sometimes one formula says more than 4 sentences for the author. Right, that's the truth. Like, honestly, the reason I'm struggling with this is because I'm just an idiot, right? Well, I'm not an idiot, but the reason I'm struggling with this is because I just never learned the mathematical notation. This is the same as, like, you know, when you read in physics something about muon decay, it's like, well, you know what muon decay is because you've been taught what muon decay is, right? If you're a mathematician, you've never heard of this before, then, like, you're going to struggle with it. And that's just what I'm doing right now. I'm struggling with it a bit. It's kind of like, you know, I also struggle when I look at p-values and stuff like that because none of the research I did ever really dealt with this, like, probabilistic, like, approach to understanding, you know, data. You know, I never really did data analysis, so to speak. Okay. So I am lost a little bit. So m is equal to 1 to infinity, n is equal to 0 to infinity. So x of n must be the current point that we are on. And then lambda. So my question here is, why does n have to be greater than m? And also, what is being intersected here? Let's just keep going. I'll probably understand it in just a second. I just need to think about it a bit. Okay, the almost sure property is with respect to the Bernoulli measure. Mu of p is equal to pn, defined on infinite sequences I from the symbolic space. Sigma is equal to 1 to n of n. In particular, if x is within lambda, which lambda is the attractor, for example, x0 is a fixed point of one of the functions, then x of n equals infinity, n0 to n infinity is almost surely a dense subset of the attractor. For the remainder, we will almost always assume that x is within, x0 is within lambda. Wait a minute, that doesn't make sense. What? No, that's not what you want them to assume in the paper. No. Wait a minute, they might be doing something different than what we want. x0, xn is n greater than m, is a set of points in the sequence after m that is xm plus 1. Yeah, so that was my question. Why are we counting up with m? Like, that means that we're counting up with n. But what I thought was that we want to be counting up with m, not n. Also, like, I do totally understand that m and n sound like totally, like, they sound the same, and I apologize. Like, I can't really change them. Yeah. Okay, but let's just keep going. So I think I kind of understand what they're saying here. Like, they're just kind of saying that when you're on the orbit, if they assume that x0 is on the attractor, then we know that every other subsequent point is also on the attractor. And so basically we're saying that the attractor is then basically the intersection of all these points put together. So, like, it's just saying, like, you know, the Sierpinski triangle, like we said before, isn't really a triangle. It's a set of points that looks like a triangle. And so that's basically what they're saying here. You know, if you have a bunch of points, for every point after x of n, where x of n is that that point where you're on the attractor. Every point after that will also be on the attractor. And here they're assuming that x naught, the very first and x, is going to be on the attractor. So essentially they're saying if we start with something on the attractor, then everything else should be. Now, that's true, but also that means that they're tackling a somewhat different like question than what I wanted to tackle. Also, let me see where this is published really quick. It was published, or was it published? Maybe it's still in the archive. It is still in the archive. I don't know where they would be. This is archive preprint, right? Yeah, okay. Obviously, if it was just submitted a few months ago, I don't really know where they're going to be, publishing this. Hey, Emrys, how are you? I hope you're having a great day. Okay. But again, this does lead me to question what they're actually asking. So maybe we'll just kind of read through the introduction and see what we can do. The chaos game can be naturally generalized to allow the indices I of n to be chosen in a IID. I see it all the time. Identically distributed, independently and identically distributed. Way. There can be closed loops on the attractor as well, so not guaranteed coverage. I don't, so what do you mean? So how does a closed loop on the attractor mean that there isn't guaranteed coverage? Sorry about that, because to me a closed loop on the attractor just means the attractor has like a circle shape, and that seems fine to me. Because, you know, like for example, if the attractor looks something like this, and then there's another ring out here, and there's another ring out here, that's still fine. It's just a 2D object that's just a bunch of rings put together, you know? So I'm not, I might be missing something. Let's see, what do we have? 1 second. Okay. So let's just keep going and see what we can do here. Again, if you guys have any comments, questions, concerns, anything like that, just let me know and I'll totally address it as soon as I see it in chat. So I'm going to try to get through at least this bit of introduction and see what we can do. So the chaos game can be naturally generalized to allow the indices I of n to be chosen in identically independently and identically distributed way. The left shift, sigma, which takes big sigma onto big sigma, which is a symbolic space here, is defined as sigma of I equals I2, 3, and a measure mu on the symbolic space sigma is sigma invariant if mu of the inverse of sigma is equal to mu dot. All right, let me read chat. Speaking of the points in the iteration, not the shape. But doesn't the randomness of the function choice mean that, like, I think I see what you're saying. You're saying, like, if we have 3 points, you know, it could just be that we go from 1, 2, 3, 1, 2, 3. We just keep going around that circle, right? That could be what we do. Which is totally fine. But, you know, eventually we'll choose a function that gets us off that circle, right? I would guess. I'm not really sure. Okay, so good news. I'm completely lost. So let's just keep going and hope that we find ourselves. The elements of I, n are sequences with the values in 1 to n. Where did that come up? I don't remember reading that. I'm so sorry. I don't remember reading anything to do with 1 to n, but that's here. Let me change the highlighter mode. That is here. The sigma. Oh, up here from the symbolic space. Right. I see. Perfect. So, the elements of I, n are sequences with the values of 1 to n. Yes, that makes sense. Penscaft, thank you so much for following. Really appreciate it. Okay. I think the next paragraph gets way easier to understand. Yeah, the next, and I think the next paragraph will also start addressing, you know, whether this paper is actually something that we need to get through or if it's something that we're getting through for fun, you know? Then we also consider the chaos game with respect to a sigma invariant measure, mu, where for every n within big N and I 1 through n within 1 through n, too many n's and big n's and little n's. I'm so sorry. I'm not doing a good job. The first n indices in the chaos game are chosen to be I1 through IN with probability of mu I1 through IN. That's just because we have a different probability for each function choice. That seems fine. Where I1 through IN denotes a cylinder set. J within sigma is equal to, where J of L is equal to I of L for L is equal 1 to N. Okay, so now that's where I'm stuck. What are we trying to do? We're basically just trying to understand, okay, this is actually what we're trying to understand. The convergence rate of the chaos game. That's actually perfectly what we're trying to understand. Behind the next dune will be an oasis probably. I feel ya. That's kind of where I'm at. I'm not very good at getting through mathematical notation, which means I just need to get better at that. And that's totally fine. I acknowledge my faults here. But essentially what we're trying to do is if we have a bunch of points in space, right? And we are following something known as a chaos game. The idea with the chaos game is, let me just show you a video really quick. CD videos, iterative function systems, videos, algorithm archive, iterative function systems, else here, and then MPV, Sierpinski chaos, MP4. So the idea with the chaos game is that kind of we have some sort of attractor known as the Sierpinski Triangle. If we take any random point in space, let's say this point, and we choose between a set of functions that can generate this Sierpinski Triangle, then eventually we will find ourselves on the triangle. So the idea here is that, we have 3 points in space, A down here, B up here, and C over here. And we have 3 functions, one that brings you halfway towards A, another that brings you halfway towards B, and another that brings you halfway towards C. The idea is if we take a random point and we randomly choose between one of those functions, so we choose function 1, then function 2, then function 1 again, then function 3, something like that, we will eventually find ourselves on the triangle, and after that, all subsequent points will also be on the triangle. And so the natural question is, well, okay, how close is this weird random approximation to the Sierpinski Triangle itself, right? Because clearly, it's not really the triangle, right? Because we just picked a random point, and we picked a bunch of random functions, so there is some error metric. But the question is, what is that error metric? And I don't really know if there is a good answer to that. And so that's what this paper is hopefully going to answer. The cylinder set, I is 1 to IN, is just a set of sequences with the values 1 to N, where you ensure that the first N terms are precisely I of 1 to IN. Right. I think that's fair. Okay, so I think this next bit is actually going to be readable, which is going to be good. Okay, so, but yeah, that's what we're trying to solve, and we're going to see where it goes. So, the natural question we address in this paper is given mu is the measure mu. Okay, that's what we want, some sort of measure of distance. So given mu, which is a measure of distance, how long does it take the chaos game to reach a certain resolution of the fractal? Moreover, for which mu will it take the least number of sets to reach that resolution? Okay, we formulate these questions rigorously in a moment. We are only aware of 16 and 19 that study this direction. The former is an informal investigation, with the latter work of Morris, while the latter work of Morris and the second named author answered these questions for self-similar sets, satisfying the open set conditions in the individually and identically distributed case. Our results greatly extend the scope and give additional context explaining and illustrating the results. A number of papers show convergence of the chaos game for more general iterative function systems, say 4 to 6, for example, while others show ergodic theorems for time averages along the orbit. We do not pursue these directions further here. Okay, I need to kind of think about this a bit. So this paragraph, does the full, I might, let me think, I screw up. I don't know what IID stands for. Independently and identically distributed. Every single time I try to remember what IID stands for, I fail. Like, that is, I usually am all for jargon. Like, I kind of think that jargon is a great way for people to learn a new field, because like it gives people like a tangible word that they're trying to understand, right? Like you're trying to understand boson, for example. It's like, good, okay, there's a word I can look up, I can Google, I can search, you know? Moreover, if I instead said, you know, particles of even spin or particles of integer spin, well, that would be a little bit harder for people to understand than just the word boson, right? So in general, I'm like, really in supportive of having some sort of jargon or something like that. However, acronyms are one thing that I don't like, because I never understand acronyms and I have a lot of trouble with that. So like IID, I already forgot it. I read it all the time, and every single time I forget it. It's like identically distributed. I know that's one of them, but independently is what I always forget. The independently and identically distributed. It means like a distribution, like just a random distribution that's just like well distributed. That's what it means. Like it just means there is no like I know what it means. I just can't. I don't know what IID individually, what those words stand for. So I never read it out. I'm like, oh, I know what they're looking for. And then I keep going. But I very rarely have to like sit there and think, oh, what does this actually mean? Okay. So what I'm asking about with this paragraph is, what is mu? Exactly, because I thought I understood it as some sort of error measure, but maybe I'm wrong. And a measure mu on the symbolic space sigma, that is sigma invariant, if mu of the inverse of sigma is equal to mu of sigma. Okay, let me think about that. So sigma, too many sigmas, capital sigma is 1 to n of big N. Now big N, why? Why are there so many? So there's n, little n, there's big N, and then there's script n. And script n means what? Script n means, I should have written this down, but I didn't because I just decided I didn't need to. You know, I was like, oh, I'm beyond. I understand this, you know, this notation. I know script r is a dimension, so script n must be... What is script n, actually? Let me get some water. Black bold n is a set of natural numbers. Good, okay. There we go. That makes sense. Right, because... Okay. Blackboard bold. Fair enough. Okay, so... That n is a set of natural numbers. I should have known that, but I didn't because I'm just dumb. So we're going from 1 to all natural numbers, and sigma is just that set. So we're saying sigma onto sigma is defined as little sigma of I, and I think all of the i's are just the probabilities, right? No. The left shift, sigma, the left shift of sigma, lowercase sigma, onto big sigma is defined as sigma... Oh, that's easy. That's totally easy. So sigma minus 1 must be the right shift. I think mu is a measure theory measure. So on a set and sigma algebra on that set, that could be true. Okay, let's try to figure out the measure theory mu in just a second. So in mu, so if sigma here is a left shift, does that mean sigma minus 1 is a right shift? And does that mean that mu, the measure theory measure... Okay, so the measure of the distance between the point... The measure of the distance... 1 second. The measure of the distance... I'm lost. Okay, let's look at measure theory. Mu. Right. Sigma is probably pre-image since sigma isn't bijective. Right. And just to be clear, I mean I know what bijective means, but if you could explain to the class what bijective means. I'm sorry, guys. I always forget. I suck at this stuff. I genuinely can never remember all of the terminology here. Let's go to images here. Bijective means okay, that makes sense. Yep, I get it. So bijective just means that all the points go to some other point, but like wait. Bijective equals 1 to 1 correspondence. Yeah, exactly. 1 to 1 correspondence. X squared is not bijective. Don't know what X squared means in this case. Bijective is when it is injective and surjective. Oh, man. Bijective means something that's injective and surjective. See, you guys, This is the thing, though. Like, if I'm struggling with the word bijective, which is a word that I've heard in the English language before, and I generally guess as to what it means, saying that it's injective and surjective, these are words I don't know. So it doesn't help. So x maps to x squared is bijective if you go from r plus to r plus. Okay, so I'm just going to keep going. So the question addressed in this article is a type of covering problem, which are problems with a rich history in the probability literature, originating from the classical coupon collector problem. Covering problems are concerned with the time taken for a stochastic process to exhaust its state space. In a precise sense, this depends on the model being studied. Classical examples include the first time that a random walk on a finite path connected graph visits all the vertices, and the first time that an irreducible finite state Markov chain visits all of its states. The geometric covering problems studied in 2 and 28 are closely related to our problem, except that while our sequence of points x1 to n is determined in a dynamical way through the chaos game. Fair enough. The points belonging to the sequences 2 to 28 are chosen at random in an individually and identically distributed way. Another closely related field is a study of recurrence in chaotic dynamical systems through hitting time statistics. This is concerned with the study of the hitting time of an orbit under a chaotic dynamic system to a ball which is shrinking down to a point in state space. Get some water, and let me think about how much of this paper we should be reading on stream. Because this is one of those things I do genuinely, like, I enjoy reading these types of things. I really do. But at the same time, I'm 100% acknowledging the fact that this is a lot of terse mathematics that I'm just gonna be Googling, essentially. Like this here, I mean, let me go to their conclusion and see what they're actually trying to figure out here. It's fun to struggle. Well, life's a struggle, right? Do they have a conclusion? References, question, open questions. Great. Well, thanks for giving me those. I didn't want open questions, though. I wanted a conclusion. Am I in the appendix? What am I doing? I mean, right now it's just math. Okay, that's a proof. Totally fine that it's a proof. Also, I don't think I've ever actually proved anything in my life. Okay, here we are. The paper literally gave you homework, right? You're supposed to read papers like these, making sure to verify the math is actually correct. No, I agree. The thing is, you can only do that if you understand the math, and I don't understand the math, so I can't. Okay. The papers ask how long do you have to wait until every point is on the attractor has a point near... Oh, wait. This paper asks how long do you have to wait until every point on the attractor has a point near it on the generated sequence. Wait a minute. Let me think. No, my friend, I agree with you. I know what you mean. Like, I'm 100% with you in that. Yeah, we should be checking the math. But if the global you, obviously there are people in chat that can do this, but if I am too, like, naive to be able to do it, then, I can't judge it, really. Okay, so learning balance. The question I have then, and again, naive, stupid question here. So if this paper asks how long you have to wait until every point on the attractor has a point near it on the generated sequence, shouldn't it be the other way around? So what I'm trying to ask is, I think a very similar question, which is, how long do you have to wait until every point on the attractor? Yeah, how long do you have to wait until every point in your generated sequence? Yeah, so it must be the same question then. So what I'm trying to ask is, how do you know, how long do you have to wait until every point on your generated sequence has a point near the attractor? So it must be the same question. It's just the negative of the other one. Okay. So I need to learn more math is what I'm learning. I was also hoping for some sort of metric in terms of like numbers. Like I was expecting like, should we just do this in code and just like send an email to the authors and be like, hey, we just did your paper, but like in a stupid, naive way. Like not through proofs or anything. We just literally just like coded up something that does it just to check your results or something. Like we could probably find the results that they have, and then we just double check. It's like, is this actually what we get? When we here's the simulations. Perfect. So from an applied point of view, the chaos game provides an efficient algorithm to produce images well approximating the attractors of an iterative function system. The choice of a measure mu driving the chaos game influences the quality of the image we obtain. We demonstrate this with one of the examples presented in Table 1. For any r greater than 0, consider a maximal r packing of the attractor lambda, i.e. a collection of sets of diameter r with the disjoint interiors that cover lambda. Okay, the orbit O of bold I of x naught becomes r dense in lambda once it has visited all elements of the r packing. For Bedford-McMullen carpets, we can keep track of the orbit using the collection of symbolic approximate squares of level k introduced in 25, where k is chosen so that m minus k is less than or equal to r, which is less than m of minus k plus 1. Recall that each approximate square bk of I is identified with a sequence I1 to IL of k, phi of I of lk plus 1, phi of ik, where phi of I is within 1 to m, denotes the index of the column to which the rectangle f of I of 0 to 1 squared belongs to. One step of the chaos game corresponds to the transition of the following. Jeez. My question is... Okay, let me get another quick sip of water. Man, I'm with you. I feel like some people in chat can follow this. I know some people in chat can follow this, but I'm not one of those people, nor am I technically in chat, I guess. Well, I mean, hello. I am in chat and do not understand. There you go. Okay. I want to say, is phi a totient function? Is that the Euler totient function? Is that somehow appearing, or is phi something else? Oh boy. One step of the chaos game corresponds to the transition. Okay, so Table 2 shows the cover times in the middle example of Table 1. Just find some other paper which is not written in Old Greek. Well, the thing is, I don't think there is another paper. This one here that we're reading, was created in 2021. So like literally just 2 months ago. Which is really surprising. Chaos games have been around for, I mean, honestly, almost 100 years now. Like they've been around since like the 1940s. So 80 years or something. So the fact that people are just now, getting to proofs of their, not legitimacy, but their like resolution and stuff like that. Like you can prove that the chaos game works at an infinity, but to prove how accurate it is at steps like maybe 0 to 100 is actually a relatively difficult question. And the fact that people are still answering this question in 2021, 80 years after the game has been introduced, says a lot about it. You know, they had much time on their hand because of because of Corona. Yeah, maybe follow, but I didn't understand the notation yet. Yeah, I feel like. Okay, the question is, how much time is it worth sinking? Is it worth sinking our teeth into this? Is the question. I feel like what I want to do is get the main results of their paper to understand, like, what are they saying? How many iterations does it take for us to basically do these simple fractals? And then the question is, okay, if we extend this to more like complicated fractals, again, some arbitrary fractal via fractal compression, does the same apply? Or is this like hyper-specific on the Bradford-McMullen sheets or carpets? That's kind of what I'm trying to understand. And if I can understand that, and like that's kind of where I feel like we should leave this paper. Again, the truth is I'm just kind of bad at this type of math. I should be better at it, but I really suck at this type of math. Which is why I think, like, you know, I don't know. I should be better at it. I'm not good at it. Okay. Proof of the theorem. You know what I want to do? I want to take a look at these guys' Google Scholar again. Here, there. I remember being relatively... What do these guys normally publish? So this guy, Amber 10. What is Amber 10? Amber is a collective name for a suite of programs that allows users to carry out molecular dynamics simulations. Oh, cool. Okay, that's nice. Scalable algorithm for molecular dynamics simulations in commodity clusters. Yep. Anton, a special purpose machine for molecular dynamics simulations. I'm just surprised that... Okay, what's he been doing recently? Calculating box dimension with the method of types on the convergence rate of chaos games. He's definitely doing stuff, you know? What's the idea you had for approximating the error? We'll get to that in just a second. Let me see what this guy's been doing recently. Cited by. Interesting. Yeah, okay. Fine. I mean, look at that. They seem to be doing a lot more work than I normally am. And the amazing thing is, it's not even postdocs doing the work. Like, it looks like they're the ones doing the work. Anyway, let's just keep going from there. Sometimes in the middle of like reading papers and stuff, I just snoop on the authors like that. It seems like that was a free time paper, right? And that's the thing; it's a free time paper. It's like not even. Okay, so the first one is the simulation guy. The other guy is the topology kind of guy, right? I'm almost positive that's the case. Probably topology guy was like talking to simulation guy. It was like, okay, look, yeah, probably, hey, I want to simulate this. Could you just run it? And he's like, okay. And he probably just ran it. Okay, let's see. What do we have here? The runtime of the chaos game on the same example with different vectors until it visits all approximate squares at level K. Quick weekend project. The thing is, it could very well be a quick weekend project for some people. Like, I'm so far behind that, like, you know, maybe if I understood the terminology, like, it would be a quick weekend project, you know? Let's see, what do we have here? For larger K, we expect the runtime would follow the order of the exponents, but since the number of approximate squares grows exponentially in K, it is computationally impossible to do simulations for much larger K. Okay. Let's just read what they say. They said something was computationally impossible, so now I'm interested. Dang it. Anytime people were like, oh, this is computationally impossible, I'm like, yeah, okay. Let's see if it's actually computationally impossible or not. Let's see. Maybe just code by intuition and make up some random code that works for some examples, then try to validate the idea mathematically. Yeah, like, this is kind of how most of my papers go. The author has a video on the paper. Oh, okay, interesting. I don't really want to watch it, but that's fine. Let's see what we have. It's an hour. It's an hour. Let's see what we can do here. It's not on YouTube, but is a YouTube player. He's just reading the paper. I've got a feeling this is going to be... Oh, no. I'm not laughing at the guy. Like, the guy's fine. It's just that, like... I don't know if it's probably easier just to go through the paper. I mean, he's literally just reading the paper off. So... Oh. And again, I should be able to follow. Like, I just can't. I have a PhD, for Pete's sake. Like, but you know, just because I have a PhD doesn't mean I can understand, you know, everything, you know? Let's see. So, not images on that PowerPoint. So, no images on the PowerPoint. No, now I know why I did mechanical engineering with simulation. Yeah, like, that's where I'm at as well. I'm going to try to get through at least the simulation section, so we can understand the results to some extent. But before that, I'm actually going to be right back, guys. Sorry about that. So give me just a minute or two, and I'll be right back. So, Yep, 1 second. Okay, back. Sorry about that. The song is, right now it is playing, I don't know which one is playing. It is playing, you guys are mentioning it, so now I need to, oh, it's the same song it was playing when I left. It is playing, oh, maybe you guys just can't hear the music. Josh Woodward, The Wake, This Is Everything. So, yep, it's all Josh Woodward music. Let me go over here. Over there, so my face should be on camera again. I can increase the background music if you guys want. There's no Wikipedia page, so you know it's obscure. Well, most papers that I read don't have a Wikipedia page, so I don't think it's that obscure. Okay. But yeah, all the music on the channel is from Josh Woodward. It's someone. Next can we read Shinichi Mochizuki's Proof of the ABC Conjecture. I know. Bo Forkov, thank you so much for following. Really appreciate it. I missed that right when I left. Okay, so let's try to get through this and see what we can do. Again, I just want to get through the simulation section. That's probably way too long and probably wrong. Wait, what was probably way too long and probably wrong? Sorry. Oh, the ABC conjecture. Yeah, maybe. Yeah, it could be. Okay. So, right, where did we even start? I started reading this section like before. Okay. The choice of measure mu driving the chaos game influences the quality of the image we obtain. Sure. Okay, we demonstrate this with one of the examples presented in Table 1. Okay, so Table 2 shows the cover times in the middle example of Table 1 for various vectors at two different scales of K6 and K9. The cover times are averaged out over 400 independent runs. Doesn't seem like very many. Of the chaos game when K equals 6. And averaged out over 100 independent runs for K equals 9. Maybe I'm misunderstanding what K is in this case. So, okay, maybe that's what I need to figure out. What is K exactly? They're different scales. So the approximate squares level K introduced in 25. Okay, so they want us to look at number 25 here. I love to hear Winter Garden music on your stream, but it's your choice. I tend to just have Woodward music going in the background because at this point I've listened to it enough that I can just like I can like tune it out, and I don't really like listening to music in general, so like it's something that I kind of needed just to, you know, I don't know, it needs to be something that I don't have to listen to. Life's lesson, physics. This actually doesn't have very much physics at all. It's mainly just chaos games, fractals, this type of stuff. So it's actually one of the like most difficult mathematical papers I think I've read, because I don't usually read mathematical papers. So okay, so for Bedford McMullen carpets, we can keep track of the orbit using the collection of symbolic approximate squares of level K introduced in 25. It's not finished, but I can't do it right now. Sorry, I kind of like, in a way, like broke my toe a few months ago, and like it's been really hurting for the past basically few weeks, and so I kind of wanted to give it a rest. But again, hopefully tomorrow I can get back to doing the workout stuff every hour on the hour. It's just that I have not been doing it recently because again, like I just my like foot has just been on fire and like I've been like hobbling around. So I'm like, look, maybe just take a break. Which has not been great for my psyche, but that's okay. You know, it's probably fine. Okay. What do we have here? Oh, I need to plug in my side screen. Okay, so oh, come on. I wanted to see how much battery my laptop had, because I might need to buy a new laptop. It apparently has 2 hours of battery. Because it's I've been online for 2 hours and it's now about dead. But I guess that's fine. If I did buy a new laptop, what do you guys think? I wanted to buy the System 76 Pangolin or whatever, like the new Ryzen laptop that they just came out, that they just released, but I didn't. I tried to get it and it was like I was a day too late, you know. Also, I'm really rambly today. I'm sorry about that, like really mumbly. ThinkPad. I have a ThinkPad already. It's fine. I don't mind it. But, you know, I was hoping to support a Linux developer if I could. But also something with Ryzen in it is what I was hoping for, you know? Okay. So let's keep going here. So I don't know exactly what K is. K seems to be the collection of symbolic approximate squares of level K. So this must be, my guess is, well, let's see if I can get any image here. So my guess is that, so this is plots of orbits using 3 different vectors. Terminated with the game P1 visit. Okay. No, I'm lost. Okay, let's just keep reading the simulation and see what we get. Okay. The vectors P1, and P2 are the same as in section 5.3, where P hat corresponds to the McMullen measure, which maximizes the house source difference dimension of new P, defined as the following. Okay, yep. Probably should understand the Hausdorff dimension before reading this paper. The pair P tilde Q tilde correspond to the uniform vectors 1 to n, 1 to m, respectively. In this case, we modify the chaos game to 2 dimensions and a transition step. A new map and a new column are chosen independently of each other according to P tilde and Q tilde. That is, if K is within 1 to n and L is within 1 to m are chosen uniformly and independently, then a transition step is the following. Okay. I'm not exactly sure what's happening here, but it goes from I from 1 to L, J from 1 to L, J of L to JK goes to K1, L of K minus 1. Okay, so it looks like we just took the kth iteration, we moved it over here, and then we took the Lth iteration and moved it over here. I mean, okay, give me a second. I'm gonna look at this guy's papers again. Specifically this guy's paper. No, this guy's paper. I'm gonna look at any of these. Like, it doesn't matter which one, just any of them. Year, calculating box dimension, PDF. Is this what these guys' papers normally look like? Like, am I the only one that's struggling here? Okay, maybe I'm the idiot. Because, like, yeah, maybe I'm the idiot. Yawning is so crazy. Can you explain why when we see the word or someone else yawn, we have to yawn? Actually, don't do that. It's very off topic. Did I yawn? Sorry about that. I didn't mean to. But, yeah, now I want to yawn. Okay, now I'm yawning. The second author has a prior paper. That seems easier. The second author does. Gosh, I just feel like I'm... Like, am I just... Let's see if they cited it. Let's go in here. Go down to the bottom, and we're looking for... I think the paper presupposes you have taken a grad course in analysis. Probably generates his papers from random CS paper generator. No. Like, they're definitely legitimate. Like, they worked the problem for a while. Right, but usually... Usually when reading papers, I still understand them. It's just, yeah, whatever. It's fine. I was gonna look for a follow-up paper or a paper that they cited from Jurga. Oh, see, now I'm super tired. Here's her paper. Yeah, let me take a look. Because their paper might be more relevant to what we're looking for. How long is the Chaos Game? PDF. 2007. How long is the Chaos Game? Probability vector. P is 1 to 3. I still don't know if I can even follow this paper. Like, you're like, oh, this one seems easier to follow. But now I'm looking at it, it's like, well, I don't know if that's true. And maybe I should just, like, email the folks and be like, hey, look, I'm trying to understand this. Could you, like, just walk me through it? You know, explain it like I'm a physicist, the type of thing, you know? 1 second. Because, yeah, I'm definitely struggling a bit. What is the point of what? So what I didn't expect was the following. I didn't expect that this question that I'm asking was in itself something that has generated papers like within the past 20 years. So good news. That means that we are on the cusp of human knowledge. We are on that boundary. We are pushing something forward. The question is, whether we were just beaten out by people who actually know what they're doing. And the answer seems like, yeah, we just were. Let me take a look at this paper. Let me see what the forward citations of it are. So let's go here, there, check the forward citations really quick. I think I want to do Scholar. Oh, I'm super tired. Wait, where'd you get this paper from? Has this been published? Google Scholar. Oh, it's just an archive preprint. They never published it anywhere. Isn't 2020? What? But I thought it just said it was 2007. Oh, where did I read 2007 from? Anyway, yeah, so good news. People are looking at this in 2020. I guess. I don't know if they generate any citations, though. That's actually what I'm looking for right now. How novel is it? Like, are people, like, actively requesting this information? I think 2007 is part of the archive ID number. Yes, that's it. Thank you. Let's see. 15 citations. Anyway, I'm going to look for... Let me just see what happens if... Oh, I'm so sorry. I'm really tired for some reason. I did not expect to be this tired. Just randomly, all of a sudden I got tired after someone, Linux, started talking about yawning. Now all of a sudden I'm super tired and yawning all the time. Thanks. It's not your fault, but, you know. Okay. So random walks in the group of Euclidean isometries, and self-similar measures. What I'm going to try to do is see how cited this group of papers are. Like, I realized this paper was not cited, but also it was only an archive preprint. Hutchinson in the references, it's the operator he defined behind the fractal flame algorithm of Scott Dray's. Right, so Hutchinson, so the Hutchinson operator is the set of all functions used for the fractal flame algorithm, correct. But yeah, it's all there. Like, the group is all there. Chaos Game visualizations of sequences. Genomic signature, characterization, classification of species, assess. Let me just Google Chaos Game. Screw it. Chaos Game. Let's go. And let's do Sense 2020 and see what we have here. Chaos Game optimization, novel meta-heuristic algorithm. Optimization, constrained mathematical engineering design problems using Chaos Game optimization. Deterministic Chaos Game, a new fractal-based pseudo-random number generator and its cryptographic application. People are still making stuff. I mean, this is new research. I've been rendering these in 3D with order independent transparency, rotor render, and Vulkan. Oh, super cool. Yeah. We actually Like, I think you were there even when we were doing the fractal flame stuff before. So I'm happy to hear that you're interested in that. Let's see. Identification of circ RNA. Let's go since 2017. Okay, that doesn't help too much. Yeah, so identify protein interactions by incorporating chaos game representation into PSE AAC. It looks like most of this is about the applications of the chaos game to other systems that like you wouldn't typically apply a chaos game to. So I think that's kind of where the new research is heading. It looks like most of this is biological implementations. Quantum repeated interactions in the chaos game. Well, that one's interesting. Why do we have... Come on. What is this related to? Quantum repeated interactions in the chaos game. Inspired by the algorithm of Barnsley's chaos game, we construct an open quantum system model based on the repeated interaction process. We show that the quantum dynamics of the appropriate fermionic bosonic system provides a physical model of the chaos game. Okay. Oh yeah, definitely interested. I think it's interesting to connect proof calculus with chaos games. They are likely visual manifestations. There are likely visual manifestations of theorems, etc. Yeah, actually, I what is proof calculus even? Like, this, is it like, yeah, what is proof calculus? In mathematical, proof calculus or a proof system is built into proof statements. Oh, interesting. Huh. Yeah, okay. I don't understand how this is at all related to the fractal flame method, if I'm being honest. But I'm sure you figured out how they're related, you know? Given a set of functions, we are likely to see some lemma, if you get what I mean. Given a set of functions. Oh, okay. Yeah, maybe I do. Okay. Let me just, I don't know. How long is the chaos game? We have the PDF up right here. Again, Ian Morris thanks his former teacher, John Little, for introducing him to fractals in general and the chaos game in particular at New College Swindon in the 1995-1996 academic year. In the 1988 textbook Fractals Everywhere, M. Barnsley introduced an algorithm for generating fractals through a random procedure he called the chaos game, using ideas from the classical theory for covering times of Markov chains. We prove an asymptotic formula for the expected time taken by this procedure to generate direct delta dense subset of given self-similar fractals satisfying the open set condition. I am too tired for this. Holy cow. I can't even read this right now. Given set of functions. Let me get some water. We have been kind of banging our head against the same paper for about an hour and 30 minutes. So like there is that. Like, you know, maybe I'm just a bit fried. Okay, again, we have the YouTube video. I'm gonna keep that there because we might actually find some use for that, but I'm gonna bring it over here. We don't need that. Maybe it's good to look at the Hausdorff distance. After 10 or so iterations, the error is less than a pixel, so that's how long it takes. Yeah, maybe that's what we do. Maybe just screw it. We're like 10 after... Okay, is that true, though? 10 or so iterations... Yeah, but that's... Okay, so how do you prove that, though? Well, maybe it's not... Maybe I'm not looking for a proof, right? Maybe I'm looking for, you know... How do you know after 10 iterations that you're... Given any arbitrary attractor, not just the Sierpinski Triangle, any arbitrary attractor, can you assume that after 10 iterations you're good to go? I mean, if so, maybe just screw it. Maybe just do the 10 iterations and like we don't have to worry about any of this proof or anything like that. So okay, I have been doing this for about 2 hours now. I think what I'll do, in Dre's paper he discusses it. Yeah, the problem with his paper was, I know which paper you're talking about, Fractal Flame. And he does mention that after the first... Yeah, no, I remember that statement, after the first 10 iterations. But it wasn't, like, measured. Like, he didn't explain, like, how he came to that. He just said, well, after the first 10 iterations or so, you're close enough. And, like, that's kind of how everyone does it. And so the question was, like... Yeah, I guess you can generally assume it's fine. Like, maybe this is what we do. We just generally assume it's fine. Okay, so here's what I'm going to do. I'm actually going to... I'm actually going to close stream for now. I'm going to take a second, do a tactical retreat, figure out if we even need to solve this question, or if we can hop onto a different question and solve that. Again, I was hoping to get a video out every week talking about like some interesting questions that we are tackling every week. And the question for this week was, you know, how do you tell if you're attracted to the Sierpinski Triangle? Like, how far away are you from an attractor at any given moment? But as we found, that's actually a research question that like is actively in development. Like, people are actively asking that question right now, and there doesn't seem to be a good answer to it just yet. So what I might do is take a step back, see if there's a good way to formulate that question, or maybe formulate the answer to that question, maybe try to figure out the paper. I don't know, like, I just need to figure it out. So I'm gonna do that, take a step back, and yeah, so I will be back tomorrow at 4:00 p.m. And yeah, if you haven't already, feel free to join the Discord. Let's see, who do we want to raid at the end of stream? We've got Lana, Soding. Let's do, let's see. I'll paste some of the results in the Discord. Yeah, feel free to join the Discord. Let's do Oh Bother, actually. Let's raid Oh Bother. Okay, let's go ahead and start the raid on Oh Bother. And that'll be it for now, guys. We'll be back again tomorrow, probably 4:00 p.m. Eastern, and we'll go for a bit longer. But yeah, thanks again for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I'll see you guys around next time for the next episode of Simuleos, which will hopefully be slightly less mathy, maybe a little bit more codey. We'll see. Thanks, guys. See you next time. Bye, guys.